Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. Now that we have a visual and a conceptual understanding of what limits are, we can begin to unpack how to utilize this notation alongside algebraic work. The connection between limits and algebra can be summarized as the limit laws. Now, before we get started, if you haven't subscribed to our channel yet, make sure you do that first so you don't miss out on new weekly content. Here we have highlighted the 7 limit laws. The first limit law says that if we want to find the limit as x approaches a of our function f of x plus or minus g of x, then that is the same as finding the limit as x approaches a of our function f of x, and then we can add or subtract the limit as x approaches a of our function g of x. So essentially, this is saying that we can actually split this up into 2 separate limits and then add or subtract them. The second one says if we want to find the limit as x approaches a of a constant c multiplied by our function f of x, we can actually take out the c in front and then just multiply it by the limit as x approaches a of our function f of x. The third and fourth one says that if we have 2 functions and they're multiplied together, then we can find the limit of each of them separately and then multiply them together. And same thing with division. The only caveat is that the limit as x approaches a of our bottom function, which is g of x, cannot be equal to 0. The fifth law says if we want to find the limit as x approaches a of some function raised to a power, then what we can do is we can actually just find the limit as x approaches a of our function first, and then we raise it to that power. Now the last 2, we didn't actually write down what they are, so we're actually going to be working through them. So the first one is the limit as x approaches a of some constant c. So now imagine we have a constant function c. So let's go ahead and draw that. That's our y-axis. This is our x-axis. And a constant function would just be a horizontal line. So this would be our constant c. So you can see that it doesn't really matter what our a value is because our function is always equal to c. So therefore, the limit as x approaches a of a constant c is always going to be equal to c. And then the last limit law is limit as x approaches a of the function x. Again, we're going to draw a graph for that. So we're going to draw our function y is equal to x. And that we know is just a diagonal line looking something like this. So this is our y is equal to x. So that means as x is approaching the value a, y is going to be approaching the same value because y is equal to x. So therefore, the limit for this one is going to be equal to a. And now let's take a look at how we can actually apply these limit laws. So here we want to find the limit as x approaches 2 of this expression here. So I am going to paste the limit laws from above right over here so we have access to them. And let's just make that a little bit bigger so that we can see it. Okay, all right, so we're going to use the first law to split all this up. So we can see that we have 1, 2, 3, 4 parts. So we're going to rewrite this as 4 separate limits. So that's going to give us limit as x approaches 2 of x cubed plus limit as x approaches 2 of 2x squared minus limit as x approaches 2 of 3x, and then plus limit as x approaches 2 of 1. And now for the first one, because we have a power of 3, we can go ahead and use law e here to find the limit of x first and then raise it to the power of 3. So that's going to be rewritten as limit as x approaches 2 of x, and then we're going to raise that to the power of 3. Plus, now the second one, we have a constant in front, so we're going to use our law b to pull the constant to the front, so that'll be 2 times, and then we're going to use the power law, so that'll be limit as x approaches 2 of x raised to the power of 2. Minus, same thing, we're going to use the constant law, so that's 3 times the limit as x approaches 2 of x, and then the last one will be just as is, so that's limit as x approaches 2 of 1. And now we can see that this and this and this, that's the same thing. So that one, we can use our law g, which tells us that limit as x approaches a number a for x is just equal to a. So then this becomes 2 to the power of 3 plus 2 times 2 to the power of 2 minus 3 times 2, and then the last one, that is just using our law f, so that is going to be equal to just 1. So this is equal to 8 plus 8 minus 6 plus 1. And that is going to be equal to 11. So some of you may have already noticed this. All we really did was substitute the value in. And that is what we call the direct substitution property. So what this property says is that if f is a polynomial or a rational function, and a is in the domain of f. So this is the important part. A has to be in the domain of f. Then the limit as x approaches a of our function f of x is just equal to f of a, i.e. meaning you can just substitute the number in. So for now, we said that this is only applicable for f being a polynomial or a rational function. And we can modify this in the near future once we have a better grasp of calculus definitions, and we'll be able to extend this to other types of functions. But for now, let's take a look at some examples. So to evaluate our first limit, right now we can't substitute it in because 1 is not in the domain, because if we try to sub 1 in, our denominator is going to be equal to 0. So we need to manipulate this a little bit first. And for this one, we are going to use our difference of cubes formula. So this is going to be equal to the limit as x approaches 1 of, our numerator is just x minus 1, but our denominator, we can factor this into x minus 1 times x squared plus x plus 1. And now we can cancel out the factor x minus 1. So then we end up with limit as x approaches 1 of 1 over x squared plus x plus 1. And now 1 is within the domain of this expression, so we can just go ahead and substitute it in. So that means this is equal to 1 over 1 plus 1 plus 1, so this is going to be 1 over 3. Our next example, again, we can see that 0 is not within the domain because we're going to be dividing by 0. And the trick to this one is we're going to multiply the top and bottom by the conjugate. So we're going to say this is equal to the limit as t approaches 0 of square root of t plus 4 minus 2 over t times the square root of t plus 4 plus 2 over the same thing. And now our numerator is going to be equal to t plus 4 minus 4, because that's a difference of squares. And then our denominator is t times the square root of t plus 4 plus 2. So notice how our top, we have a plus 4 and a minus 4, so which means we're left with just t on top. And then the bottom stays the same. And the reason we're doing this is because now we can cancel out the t on top and the t on the bottom. And once we cancel out the t, 0 is now within our domain. So we can go ahead and substitute it in. And this is going to be equal to 1 over 4. And now our third example, we have a fraction divided by a fraction. So let's go ahead and simplify this a little bit first. So we're going to rewrite this as limit as x approaches 3 of, we're going to have our top function, which is x squared minus 9, but we're going to factor that into x minus 3, x plus 3 over x minus 3. And then we're going to multiply it by the reciprocal of the denominator. So that's going to be x minus 2 over x plus 3. And by doing this, we can see that we can cancel out the x minus 3 on top and bottom, as well as the x plus 3. So then this becomes just the limit as x approaches 3 of x minus 2. And because 3 is within the domain of x minus 2, we can go ahead and substitute it in, and this is equal to 1. And now our last example deals with an absolute value. So if you recall, absolute value of x is equal to just x when x is greater than or equal to 0. But if x is less than 0, then the absolute value of x is equal to negative x. So that tells us we're actually dealing with a piecewise function here. So the expression that's inside the absolute value sign here is x minus 4. So that means our function, the absolute value of x minus 4 over x squared minus 16 can be split into a piecewise function, one for which x is greater than or equal to 4, and the other one is going to be x is less than 4. So when x is greater than or equal to 4, then the absolute value sign does nothing. So this would just be x minus 4 over x squared minus 16. But when x is less than 4, then the absolute value sign is going to flip the sign. So that means our numerator is going to be negative x minus 4 over x squared minus 16. And we can actually simplify each of them because our denominator is a difference of squares. So this is equal to, if we factor a denominator, that would be x minus 4 times x plus 4. So which means the first piece is going to be 1 over x plus 4. So this is for x is greater than or equal to 4. And then the second piece is going to be negative 1 over x plus 4. And this would be for x is less than 4. So now because we want to find the limit as x approaches 4, and our function is a piecewise function, one piece for x greater than or equal to 4, and the other piece for x is less than 4, we need to go ahead and find the one-sided limit, one for approaching 4 from the right-hand side, and the other for approaching 4 from the left-hand side, because we're going to be using the two different pieces in these two different scenarios. So if we want to find the limit as we approach 4 from the left-hand side, that means we're approaching 4 from numbers that are less than 4. For that, we're going to be using this piece right over here. So this is going to be limit as x approaches 4 from the left-hand side of negative 1 over x plus 4. And this is going to be equal to negative 1 over 8. Now if we approach from the right-hand side, that is going to be 4 from the positive side. And for that part, we're going to be using this piece over here. So that means the function here is positive 1 over x plus 4. And we can substitute it in, and this gives us positive 1 over 8. So since the limit as x approaches 4 from the negative side of our function f of x does not equal to the limit as x approaches 4 from the positive side of our function, we have the limit as x approaches 4 does not exist. And now let's go ahead and do a quick recap of what we covered in this video. We went over our limit laws and saw how they gave us permission to break complicated limits into simpler pieces. In particular, these laws let us move limits through addition, subtraction, constant powers, and products, as long as the individual limits exist. We saw how for polynomials and rational functions, these limits often reduce to direct substitution, as long as the function is defined at the particular point. When you're faced with a problem where you can't direct substitute because the function isn't defined at the point, you can try factoring, canceling common factors, and rationalizing to see if you can manipulate the expression into something that you can work with. And in our last example, we saw how limits involving absolute values will require us to rewrite it as a piecewise function, and we must evaluate the limit from the left-hand side and right-hand side, and if these one-sided limits are different, then the limit does not exist, even if each side is well-defined. And now it is your turn to give this a try. Can you evaluate the limit on the screen here? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on limits in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.